Hello, this time I just want to say a little bit more about how we can use superposition to represent real signals in terms of cisoids. The first point I want to draw your attention to is that a cisoid, a general cisoid, can be written in terms of an amplitude A, that's the distance from the origin of the Argand diagram, times e to the j omega t plus theta, a phase term, where theta is the phase of the cisoid at time t equals 0. Because when t equals 0, omega t is going to be equal to 0, and we're just left with a e to the j theta, that point there. Then, as time starts to increase, this phase term will start to increase, the cisoid will start moving around the origin like so. Now I could write that in this form: a e to the j theta times e to the j omega t, just using the property of exponentials that e to the power of x plus y equals e to the power of x times e to the power of y. And this is a complex number with an amplitude equal to the amplitude of an oscillation, and a phase equal to the phase of the oscillation at time t equals 0. So this complex number contains information about the amplitude and the phase of the oscillation, but not its frequency. Now we've seen something very like that before. Remember phasors? Phasors were complex numbers which we used to represent real sinusoidal oscillations. And a phasor is related to the real sinusoidal oscillation by multiplying the phasor by e to the j omega t and taking the real part. So if we take this complex number, multiply it by e to the j omega t like this, and take the real part, we should end up with a sinusoidal oscillation. And we do. The real part of a e to the j theta, e to the j omega t, just works out to be the real part of a times e to the j theta plus omega t, which is the real part of a times cosine omega t plus theta plus ja sine omega t plus theta. And that is just equal to this, because this is completely imaginary, and if we're only considering the real part, we're just left with a cosine omega t plus theta. That's a real sinusoidal oscillation. So this complex number up here can be considered to be a phasor representation of this waveform. And this waveform is the projection of this cisoidal oscillation on the real axis. If you just consider the real part of this oscillation, it'll start here, go down to there, back up to here, down to there, back up to here, and so on. Just the real part, which is the part we can observe in the lab. That is the oscillation that is represented by this, treating this as a phasor. But of course, this whole cisoid is not a real oscillation. It's a cisoid. It's a complex oscillation. And we need the imaginary part of this oscillation as well in order to use the complex impedance theory that we've derived earlier. So we're not quite at a very simple method for using these complex impedances yet. What we can use, however, is superposition. We have this formula for expressing a complex oscillation in terms of its real and imaginary parts. If we just look at what happens if we replace omega t with minus omega t, that would correspond to an oscillation which is heading round in the other direction, because the phase is now decreasing as time is increasing, with a negative value of omega. That would give us this. Add these two together, and we get this expression for cosine omega t in terms of two sinusoidal oscillations. If we're trying to deal in general with a real oscillation which has an amplitude and a phase like this one, then we'd have to consider the sinusoid A times the exponent of j omega t plus theta, and that's equal to A cosine cosine omega t plus theta plus j A sine omega t plus theta, and A exponent with a negative version of this phase term, so minus j omega t plus theta. That would work out to be A cosine minus omega t plus theta, but cosine is an even function, so the cosine of minus x equals the cosine of x. That would just be equal to cosine omega 2 plus theta again, plus j A sine of minus omega t minus theta, but sine is an odd function, so sine of minus x equals minus sine of x. So we could just replace that with minus sine omega t plus theta. Add up these two equations, we get A exponent j omega t plus theta plus exponent minus j omega t plus theta, that's adding up these two terms, equals, adding up these two terms on this side, the sine terms would cancel, we'd be left with 2a cosine omega t plus theta. Or in other words, the real oscillation that we're trying to represent in terms of sinusoids, that would be a cosine omega t plus theta, is equal to a over 2 times the exponent of j omega t plus theta, that's one sinusoid, plus a over 2 times the exponent of minus j omega t plus theta. That's another sinusoid. So we can always express a real cosine wave in terms of the sum of two sinusoidal oscillations. And we know how to solve circuits if we can assume that the voltages and the currents are sinusoidal oscillations. So all we'd have to do to solve a circuit, if the voltage source was a real cosine wave like this, is to separate that cosine wave into two sinusoidal oscillations, one with a frequency of omega and one with a frequency of minus omega. Solve the circuit for both of those sinusoidal oscillations, and then use superposition to combine those two results. And provided the circuit is linear, that should give us the result for a real sinusoidally varying source, without any requirement to do any calculus. Next time, we'll do an example of this technique.